This is a battery out of a 2007 Honda Civic IMA, one of those early hybrid type vehicles. If you have one of these and your IMA light comes on, this is a reasonable suspect because these batteries go bad over time. They are in fact notorious for it. I have just restored this battery from about 20% capacity up to about 80% capacity without replacing any cells. And if you're in luck, you might be able to do this as well with some not particularly specialized equipment, because what happens with these batteries is the vehicle has no way to balance the cells. Inside, this big hunk is made up of a bit over 100 normal D-size nickel metal hydride batteries like you'd use in an old flashlight, and since these are individual batteries, they're going to behave a little different over time, and since the vehicle doesn't know the difference between each cell, it just sees the whole battery as a whole. When one cell goes bad, that weak cell is going to limit the capacity of the entire pack. And that had happened in this case. Nothing had actually broken, all the cells worked, it's just that a few of them were about halfway charged while the others were full. And when that happens, the vehicle can't charge the bad cells because the other ones are full. How would it be able to push any power into them? And you fix this by taking the battery apart at least to this stage and manually discharging and charging the battery up a few times. And the equipment needed for this is not very sophisticated at all. The bare minimum you're going to need is some way of discharging the batteries. Thankfully, they are set up in a way so that each pair of terminals, so you can see there's a red one and a white one, these have a positive and negative ends of a roughly 15 volt string of cells. You have 12 cells in series here. So the voltage range is 10.8 to about 18 volts. So you could potentially use 2 car headlamps in series to discharge these, as long as you keep an eye on the voltage. You're also going to need a way to recharge them. That's going to be a power supply capable of delivering 18 volts at 5 amps. You need to have a current limit. You can't use like a wall wart AC adapter thing. It has to be a lab power supply. Car battery charger will not work. You have to be able to adjust a specific voltage and current setting. So I would say this one only goes up to 4, but yeah, that's a reasonable setting to use. Finally, you're going to need a multimeter with a thermocouple, because the way you make sure a cell is fully charged is through its temperature. Since we're really seeing the voltage across each individual cell, we're treating them as 12 cell blocks. Nickel metal hydride batteries, they don't get very hot while normally charging, but when they're full, the temperature spikes up. So the way I've done it is I've monitored the temperature. While I've been charging these, I've terminated the charge when they get to about 40 C. This guy has been off charge for a while, and the heat is just slowly creeping out. So the final thing you're going to need is somewhere to cool the cells while working on them if you're going to use high current, as I have. So I've just got a huge fan blowing through the pack, and that just makes the whole process go so much faster, since it takes longer for the cells to get up to the maximum temperature. You're able to push more capacity into them before they overheat, and that's really the trick to this, is making sure you get as much energy into the cells before they overheat, and doing that a few times. So you can be super simple, super high-tech about this however you want. I've obviously been quite high-tech. So to go into a bit of a detail on how these problems occur, I have this data logging software on the PC, and what you're looking at in this graph is the discharge curve of one of the cells when I initially got this battery pack. So an ideal battery will go kind of straight and then bonk straight down once it's empty. But as you can see, we have these weird humps in the middle, and these are points where single cells in the battery are completely depleted. This is about 1.2 volts between those two levels. So what's happened is, as I started to discharge, all the cells are fine, then the weakest one, completely empty. And now that cell has nothing more to give. Our 14.4 volt battery has turned into a 13 point something volt battery, and then moments later the next one has gone bad, and our 13 point something volt battery has turned into a 12-ish volt battery, and then those cells are just not doing anything anymore, while the final few, which are still good, which have high capacity, keep pushing until finally the low voltage cutoff threshold is reached and the discharge is terminated. And often when this happens, these cells are not actually broken, they're just half charged. So by then pushing a bunch of current through this pack and charging it as much as you can until it overheats, you gradually make this go further and further to the right. 2 or 3 charge-discharge cycles seems to do the trick, and finally you will end up with a curve that's just smooth until all cells at once plummet at the end, and that's how a good new battery behaves. So let's go through step by step how you would go about doing what I've done to this battery from start to finish. So the first thing I recommend you do is you measure the voltage of every single cell. Between each of these points you should have no less than 14.3 volts. These are all connected in two like sticks in series, so between the right ones of these you're going to have a voltage, between the wrong ones you're not going to have a voltage, so you need to just check. You can see easily on the back which ones connect to each other. So once you figure that out, you just go through, make sure every voltage is over 14.3 volts. There's 11 of these pairs, and this one I know is fine since I just fixed it. The reason you want to make sure it's over 14.3 is if it's below 14.3, then it's very likely that you have a cell, one single battery in there, that's completely dead, a short circuit. And if you have that, you will need to replace that stick. You can try just forcing a bunch of charge into it even if it's below 14.3, but there's a very good chance you will never make that particular set of cells good again. So keep that in mind. But if you're lucky like me and all of them are 14.3 or above, you can proceed to the next step. And what I did was I connected up a charger that's I used my lab power supply, which puts out to 4 amps. So I charged one of these cell pairs at 4 amps with a thermocouple stuck in there, and once the temperature reached about 40 C, I terminated the charge. Having the fan blowing air through the pack really helps. That made everything work so much better. I figured that out after a couple of cells. And once you've reached the point where the cells are just heating up, they're not accepting any more charge, you can go on and start discharging them. So I've just got my big dummy load connected up, and if we bring the ammeter there and turn on the discharge, I've been discharging at 8 amps. So let it do that until it reaches 10.8 volts across the cell. You absolutely do not want to have less than 10.8 volts across these cells, because once you go below 10.8, that's the point where you're guaranteed to have all cells depleted, and discharging below that will damage the cells. So if you're just using like a car headlamp, you really need to be like a hawk on this voltage. It's not going to take long. It could take just between 10 minutes and half an hour to discharge the cells to 10.8 volts, and as soon as it goes down to 10.8 you disconnect and turn the charger back on, recharge it at 5-ish amps until it gets to 40 C again. It's a good idea to let it cool down for a while there, since it's usually quite hot after the first cycle, and the cooler the cells are, the happier they are. And you should note the time it takes to discharge the cells. If you're lucky, it's going to take longer and longer to discharge, meaning you're getting more and more capacity every time you discharge and recharge and discharge and recharge. And on this pack, I've discharged and recharged every single cell twice, and that's all it took. But I have reasonably powerful chargers, and I have this huge fan cooling it. So if you have dodgy equipment, it could take a couple more cycles, since you're not working the cells as precisely as I am. But I would not expect it to take more than maybe 4 cycles at the most. The important thing to look out for is once you've reached the point that you're not gaining more than like 0.1 amp hours per cycle, you really shouldn't keep on doing it, because then you're just wearing the cells down. I gained about twice the capacity each cycle. This cell went from 2 amp hours to 3.5 amp hours to 4.5 amp hours. Over its 2 cycles and 3 recharges, so I would not expect it to take much more than that. And yeah, that's basically it. Super important that you actually do use a thermocouple which you shove in here, because an IR gun will not work on these, because the cells do not conduct heat out to either end of them very well. So these can be quite cool. Like, none of this is hot, but if we take a look at the thermocouple, the cell up here is actually well over 40 C, and that's no good. So you really need to shove a couple in there with every, just by every cell you're testing. There's a bunch of holes in the front here. It's really quite easy to do. You can also kind of poke your fingers in around the back and feel some of the cells along the edges, and on the bottom side of the battery in my case you can feel the whole top row. But yeah, temperature is important, and that's pretty much it really. Once you've got the cells to roughly the same capacity as far as they'll go, you just put it back together and shove it back in the vehicle, and hopefully it's going to be good. Nothing more to it, so yeah, hope that was useful. Thank you for watching, and good luck.